In this video, we're going to generalize the idea of divisibility inside the integers to divisibility inside any integral domain. So throughout this video, we're going to let D be an integral domain, and we're going to assume that the 1 in D is not the same thing as the 0 in D. So our integral domain has at least two elements. We're going to start with a basic definition. If A and B are elements of D, and there exists a C inside D such that B is equal to A times C, we say that A divides B, and we write A divides B this way. Now it's important to realize, let me clean that up. It's important to realize that the statement A divides B is a true false statement. And what I mean by that is this. A divides B is true happens when there does exist a C inside our domain such that B is equal to A times C. A divides B is false means that there is no C inside our domain such that B is equal to A times C. And in this particular thing, if A does not divide B, we write A does not divide B for A does not divide B. And this particular notation is mimicking the notation for divides in a number theory situation exactly. Well, I want to look at a couple of consequences about this definition. So let's first of all look at this. Suppose we actually take a unit inside our domain. And I am going to let A be any other element of the domain. Then it turns out that we can write the following. So look at this. A is certainly going to be equal to A times 1. And since U is a unit up here, that's going to say that we can rewrite that 1 as U inverse times U. And this is because U is a unit inside my domain. But now I can reassociate. So I've now got A is equal to A times U inverse times U, and this element is inside my domain D, and so that last statement says U divides A. In other words, we've just proved the following proposition. So we just proved this proposition. If U is a unit inside my domain and A is any other element inside the domain, then U divides A. In other words, I can state this in English. Units divide all elements of the domain. And that's an important thing to keep in mind about divisibility. There is another vocabulary word that I also want to introduce that is based on this idea that units divide everything, and it also ties something up together with this idea. So we're going to have one more new definition in this video. We're going to let A and B be any elements of our domain D, and if there is a unit inside the domain, and let me get my notation correct. So if there is a unit inside the domain such that A is equal to B times that unit, then we call A and B associates inside the domain D. Now, there's another thing that I want to note here, too, that's very important. We have A is equal to B times U, where U is a unit. That's going to happen if and only if I can post-multiply this equation by U inverse and get A times U inverse is equal to B. But that's going to say that this is where U inverse is also a unit inside D. And so this is going to say that being associates is a similarity, has a similarity property. In other words, this is going to say if and only if B and A are associates of each other. So in some sense, it's important to realize that the property, we can write this away. Let's write A is similar to B for A is an associate of B. And what we just got done showing is that this particular relation is symmetric. On the set of elements inside our domain D. Clearly, this relation is also reflexive on D, since any element is equal to A times 1, and 1 is a unit. Let me write that more properly. 1 is a unit inside D, and so this would say A is indeed an associate of A. Finally, it's worth noting that this is an associate property is also transitive. So let's look at that. So it is transitive on D. In other words, if A is an associate of B and B is an associate of C, then A is going to be an associate of C. Well, the proof of this would go along these lines. A is an associate of B means that A can be written as B times U1 for some U1 inside the set of units. B is an associate of C obviously says that C is equal, not C, it says that B is equal to C times U2 for some U2 inside the set of units. And so what we get then is A is equal to B times U1, but B is equal to C times U2, and then we have that times U1. And it turns out that it is pretty easy to show that U2, U1 is indeed a unit inside our domain. And hence, we have that A is indeed an associate of C. So what this says is the following. So, is an associate of is an equivalence relation on our domain D. And that's an important idea.